Hi everyone, welcome back. So in our previous lectures, we built a 1D convolutional kernel. Basically, we used a two-stage loading strategy to perfectly pack our shared memory. If you forgot it, let me try to record it for you. So this is the first stage. We just put the first 256 elements into the shared memory. Okay. But since we have the hello cells or ghost cells, we have to put 6 more elements, right, into the shared memory. So some of these threads have to do some additional work. Okay. So you can feel it was a masterpiece of indexing, but it also makes things complex. Today, I want to ask a question that every senior engineer must face in the real world. Is that kind of complexity actually worth of it? So when you write the codes that require complex offset calculations, like like here, I think I spent some time to explain the offset as well as the g underscore offset in previous video. So when you try to do this complex offset calculation and the two-stage barrier synchronizations, you increase the risk of the bugs, and you make the code much harder for the next engineer to maintain. So what if we could get, let's see, 90% of the performance with only 10% of the effort? Today, we're going to do exactly that by trusting our hardware. To understand that, let me add more information about the hardware. So in modern architectures, the hardware L1 cache and the software managed shared memory actually live on the exact same piece of the ultra-fast SRAM. So in our previous version, we treat the GPU like it has no cache at all. We manually load every single kind of hello elements into the shared memory. But what if we just didn't? What if we just let the hardware to do its job? Okay, so let's see the fourth version of our kernel. It is under the 1D underscore cache directory. So here is a key point. Okay, so we still kind of declare some shared memory, but now no complex offsets, no padded sizes. Okay, look at this elegance. So we no longer force the 256 threads to load 262 elements. So thread 0 load element 0, thread 255 load element 255, because we still keep our CPU side 0 padding. Okay, so still 0 padding. Yeah, remember we have some 0 paddings here. Okay, yeah. So then the left side padding is kind of handled naturally, but what about right hello? So we intentionally left it behind in the global memory. So what does that mean? Okay, it's here. It's here. So in previous version, we do not have this if-else condition, but now we have it. Okay, so this if-else statement checks if our thread is trying to read parsed data we loaded in the shared memory, right? If it's parsed data, let's see. Okay, we just fall back to reading directly from the array in the global memory here. Now I know what you're thinking. Okay, so didn't you tell us that if statement causes the warp divergence? Yes, they do. But let's quantify the damage. So our block has 256 threads, which is 8 warps. Because our mask length is only 7, only the threads at the very end of the block, threads 250 to 255, will even trigger that kind of if statement. That means only 8 warp divergence. the first 7 warps just run at maximum theoretical efficiency. Furthermore, when those kind of last few threads reach out to the global memory, the first reads put the hello chunks into the hardware L1 cache, as we mentioned. Then the subsequent reads from other threads in that warp will instantly hit this L1 cache. So we're letting the hardware manage the complexity for us. Okay, so yeah, so this is the key point here. If it's not beyond to the block dimension.x, then we just load all these things from the shared memory. So that's the key point. I think with this, we can try to compile the code and run it. Here it is. I already compiled the code for 1D cache, and previously I also have some thing about the 1D tiled version, right? So let's try to compare it only for the kernel time. So now it takes kind of 18 millisecond, right, microsecond. Previously we have the 14 microsecond. Of course, we know it kind of we lose some efficiencies, but that's okay, right? We simplify the code a lot, and no free lunch, and we pay some kind of efforts in the computational efficiency, but that's okay, right? So yeah, so that is I think the final story of this version. Basically, the thing is, you can try to rely on the hardware's cache management instead of writing complex kind of local variables to manage the cache for yourself in the shared memory. So with that, I think that's the end of this video. In next video, we will go to the 2D convolutional kernel. Thanks for watching.